Hi everyone, welcome to the second lecture of this force sensor which we are discussing in our 7th week. This is the course on microsensors and nanosensors. In today's class, we are going to discuss about capacitive force sensors. So you already have seen some sensors which is based on capacitive principle. Okay, so the basic layout for a capacitive micro force sensor is something like that. You have top gated structure and a bottom gated structure which is of some metal. Okay, this metallic structure is again deposited by some physical vapor deposition or the chemical vapor deposition, and you have a gap. In this gap you have either air or some dielectric material, right? We already have seen that this kind of structure uses the parallel plate configuration, and the formula is very simple. It is epsilon naught and into epsilon r multiplied by a by d. A by d we have already seen is a geometry factor, right? Geometry factor of this device. So C is equal to epsilon naught epsilon r into g, which is the geometry factor. In this equation, epsilon naught is the permittivity of the free space, while if you are using a dielectric material, so you have to introduce this epsilon r, which is the relative permittivity. A is the plate's area and d is the distance between these two plates, right? So when you apply a force, what happens is the gap between these two plates changes. Accordingly, this d value change, right? And then you can calibrate your sensor based on applied force and you can map it to the capacitance value. Okay, so what you are doing is you are applying some force. Okay, by applying this force, what is the change in the capacitance value? This capacitance value is changing because this d value is changing. Okay, so you measure the variation of the capacitance and then you calculate the value of the force. Okay, so force causes the plate displacement, which changes the plate gap. Okay, and because of that there is a change in capacitance. Okay, usually these capacitive force sensors are mostly based on MEMS technology. Okay, and in MEMS, fabrication of this kind of device is quite possible. Okay, so the COM drive capacitive force sensors is majorly based on MEMS technology. Okay, so let us discuss about a COM drive type of capacitive force sensor, which is of utmost importance because of its large applications. Okay, so a COM drive capacitive sensor is made up of two set of finger like electrodes. Okay, you have a fixed electrode configuration and a moving electrode configuration. Okay, these both the electrodes are made up of some metal. Okay, mostly made up of gold or platinum. Okay, so this, as the name suggests, this fixed electrode has fixed finger sets. Okay, so these fingers of these electrodes are fixed. Another finger set, which is of this moving electrode, is set to be free. Okay, and this moves along a single axis, or sometime it can move along multiple axes. When I say multiple axes, I mean to say that, so this movement we are seeing along with the fixed electrode, right? So the moving electrode movement we are seeing with respect to the fixed electrodes. Okay, so when I say it can move along one axis or multiple axis, what I mean to say is this moving electrode can move in x direction. So if it is moving in x direction, let us see how it will look. Okay, see, I have this fixed electrode configuration. Now I am considering that this moving electrode can move in the x direction. Okay, so this is the initial position of the electrode, right? Now if it is moving along x direction, say this is the final position of the electrode. Okay, and this is how it looks. So this finger has came here, this one has transformed to here, this come here, and this comes here. So it looks something like this. This is the movement along only x-axis. Okay, now consider that, so these electrodes has moved from this position to this position, right? Now there can be one more movement which is along z axis. Okay, now if I consider that this point is fixed, okay, and this is moving along z axis, okay, so you can consider that this will looks something like this, right? So the electrodes, if I am fixing this point, this is kind of moving in the z direction, all right? So because of that, this will be at certain angle with the fixed electrode. This case is more complicated. In this course, we are going to see the two cases where the movement I mentioned that is along x-axis and along the y-axis. Now, these two sets of fingers, the fingers of the moving electrode and the fingers of the fixed electrode, lie in the same plane and are oriented parallel to the substrate. It makes sure that it can be fabricated by some existing fabrication technology. Okay, these fingers are also pre-engaged with the initial overlapping area. Okay, this is the initial assumption for the case of COM drive kind of capacitive force sensors. Okay, the capacitance is generated between the vertical side walls of the adjacent fingers. Okay, the capacitance is generated between the vertical side walls of the adjacent finger. So this electrode of the fixed electrode, or this comb, this finger of this fixed electrode comb is adjacent to this finger. I am calling it finger 1, 1M, 2M and 3M. I am calling this 1F and 2F. Alright. Even if I am not considering any movement of these fingers, what I can say that finger 1M and 1F is constituting a capacitance. Finger 1F is also involved in making a capacitance with finger 2M, right? Similarly, finger 2M is also involved with a finger 2F of this fixed electrode to make a capacitance. Okay, so I have, say, capacitance C1M 1F, which is forming here. I also have a capacitance C1F 2M. I also have a capacitance C2M 2F, right? I have another capacitance which is C2F 3M and so on, right? These can be the different capacitances which is getting formed in this COM drive kind of capacitive force sensors. Okay, now these capacitances can change. So this is the initial capacitance that we have seen C1M, C1M1F, C1F2M, C2M2F, C2F3M. This is the initial capacitance of this system, if you take consideration of all these capacitances. These capacitances can change by changing the lateral overlap area between the two set of the COM fingers, or by changing the transverse gap between the two fingers. I am not considering any rotation right now. Okay, so there can be two ways by which I can change the capacitance of this system. Okay, one is by changing the lateral overlap area between the two set of the COM fingers, while it can also be changed by changing the transverse gap between these fingers of the fixed electrode and the moving electrode. Okay, the two opposite side walls of the COM fingers in the overlapping region form a single capacitor with some capacitance value. Okay, the two opposite side walls of the COM finger in the overlapping region, we have seen, forms a single capacitor with some capacitance value. This value can be given as, if I am not considering any dielectric material, I am considering only air. Okay, the value can be epsilon naught into L naught into T divided by G, right, where L naught is the initial overlapping distance between the fingers, T is the thickness of the finger, while G is the initial gap between the fingers. I am considering that the finger thickness of the moving electrode as well as the fixed electrode is same. Okay. Now, the total capacitance of the COM drive sensor is the sum of the capacitances of all electrode pairs formed by the COM fingers. Okay, please note that I am not talking about individual electrode fingers, but I am talking about number of pairs. So N is the number of electrode pairs. Okay, so now the total capacitance can be given by C single multiplied by N, or if you remember, the C single was epsilon naught L naught into T by G. So if you multiply this term with N, or which is the number of pairs, okay, you will get the total capacitance. All right. So this is the fundamental behind COM drive capacitive force sensors. You have already seen that the capacitance can change when there is a transverse movement of the moving electrode, or there is a lateral movement of the moving electrode. So based on this, you have two operating modes of this COM drive capacitive force sensor. So there are two modes. One is transversal COM drive force sensor and another mode is lateral COM drive force sensors. We call it transversal mode and the lateral mode. Let us see how they operate in these two different modes. Okay, so we are seeing this as two different entity. One is transversal COM drive force sensors, while another is lateral COM drive force sensors. Okay, let us see first the transversal COM drive force sensors. Okay, in the transversal COM drive force sensor, the applied force changes the gap between the COM fingers. Please note that you are applying force on the moving electrode, something like this, so that this electrode, so please note that the solid line is the initial position, while dotted line suggests the final position of the moving electrode. Okay, so you are applying a force to the moving electrode. Say for example, if you want to measure the force, you will apply it to the moving electrode, okay, intentionally. So you apply this to this moving electrode, and this solid line, as I have mentioned, is the initial position, while dotted line is the final position. Okay, so if this position changes to this dotted position, okay, what you are doing is you are changing the gap between the COM fingers. Okay, now the force sensitivity is improved using this kind of configuration. Okay, you can calculate the capacitance change by the equations that we have just seen just now, but the force sensitivity of this kind of structure is improved, as compared to the other configurations. Okay, also there is a non-linear relationship between the force and capacitance changes. Okay, so the relationship between force and the capacitance change delta C is not linear in this case. Okay, and the useful range of the displacement is very limited in this case. Okay, however, the resultant relation between the force and the capacitance change is non-linear and the useful range of displacement is limited. Now, what I am talking about the non-linearity of this sensor, but please note that even the sensor is non-linear, as we have discussed in the module 1, we can have a linear region of the sensor where of course you already know the piecewise linear approximation. So from the transfer function you can find the linear region of the operation. Okay, now the second kind of capacitive force sensor is the lateral com drive force sensor. Okay, the lateral com drive force sensor is based on varying the overlapping area between the electrodes in response to the applied force. Okay, so here the movement of this moving electrode is in the lateral direction, right? This will move in this direction. Okay, now the x-axis movement is not there. Okay, so the final position suggests the movement of this solid part to this dotted part. Okay, so initially it is here, finally it is moved to this position, right? So advantage of this configuration over the previous one that you have seen, the transversal com drive force sensor, is the previous mode of operation was non-linear force sensor configuration, while this configuration offers a linear relationship between capacitance and the overlapping area. However, it's sensitive to the variation in the gap. Okay, so this is all about the com drive kind of capacitive sensor. Okay, now let us see some advantage of in general the capacitive force sensor. This is just one configuration. This can come in other configurations also, but what are the advantages of using capacitive force sensors, particularly the one we have seen already, the strain gauge based capacitive sensor. So what advantages this capacitive force sensor offers over the previous one? Okay, as well as other force sensors like piezoelectric or other force sensors that we are going to discuss in the next lectures. Okay, the biggest advantage of this capacitive force sensors is its high sensitivity as compared to the strain gauge one. Okay, the energy consumption of this capacitive force sensors are also not very high. Okay, it's low or it's moderate, so that is one of the advantage. Okay, the frequency response of this capacitive force sensor is the biggest advantage of this kind of sensors. Okay, so the frequency response of this capacitive force sensors is pretty good. Okay, the spatial resolution of this capacitive force sensor is very high. Okay, the dynamic range is also very good in case of capacitive force sensors, and good thing about them is they are not much sensitive to the change in the environment because you are not using any glue or any other kind of adhesive here. Okay, so capacitive force sensors are also widely used because of their large bandwidth, as we have already seen. Okay, the robustness and drift-free measurement capability of this capacitive force sensor make them usable in case of medical devices and other IoT applications. Okay, their detection accuracy in micronewton or even in sub-micronewton is one of the biggest advantage and make it useful in many other automation and other applications. Okay, however, the sensitivity of the capacitive force sensors depend on various parameters. First of all is the plate area. Okay, then it also depends on the initial gap. Okay, if you see, we have assumed the initial gap already in the in our discussion. So the sensitivity highly dependent on the initial gap of the fingers. Okay, then material stiffness is one of the parameter that governs the sensitivity of this capacitive force sensor. Okay, they are highly sensitive when you have flexible structure and if the initial gap is very low. Okay, so for flexible force sensor or flexible micro force sensor, which is in demand particularly because of wearable devices coming into picture because of the flexible electronics rise. Okay, this micro force sensors or flexible micro sensors has also been in demand, and their sensitivity is usually higher if you keep the initial gaps as small as possible. Let us see one example of flexible force sensor. Okay, so you have basically a flexible dielectric material. Sometimes you may also have flexible electrodes. Okay, but what we are seeing here is the flexible dielectric material, and again as the previous case, in the previous case we have seen that there was a fixed comb structure and then there was a moving electrode. Similar to that, in this flexible device you have a flexible dielectric material and you have a fixed plate while another plate is movable. Okay, so you have a movable plate also. Okay, now when the dielectric is compressed, the area of the electrode increases. Okay, however, if you see, the total volume of the flexible dielectric will remain constant. Okay, so we know that from the parallel plate configuration, C is equal to epsilon naught epsilon r into A by d. Okay, if I multiply this d to the numerator and denominator, I have epsilon naught epsilon r A by d. I am multiplying this numerator and denominator with d. Okay, I have epsilon naught epsilon r A into d by d square. Okay, area into this d will give you the volume. Okay, so I can write this as capacitance equal to epsilon naught epsilon r into v by d square, right? In this equation, again the letters has their own meaning. A is the area of plates, d is the distance between the plates, epsilon r is the relative dielectric constant, while epsilon naught is the vacuum permittivity, c is the capacitance of the sensor, and v is the total volume, right? So for a small change around an initial area A naught and an initial thickness D naught, the change in the capacitance is found from the partial derivative of C with respect to D, or delta C can be given as del C by del D, where D is approaching to D naught, right? It's not 0. We are not considering it to be 0. Okay, so D is approaching to D naught. Okay, so if you put this value of C, which is epsilon naught epsilon r into A by D in this equation, okay, I can write that del C is equal to, delta C is equal to del C by del D. Okay, or if you do the partial derivative, you get minus 2 into epsilon naught into epsilon r into A naught by d square into del D. Okay, in the situation where the material is used in its linear range, the equation for the del D or force, you can say, is equal to del D is equal to F into D naught by A naught into E effective, where E effective is the effective Young's modulus. Okay, so from this equation I can easily calculate the force, which is equal to del D into initial area into the effective Young's modulus divided by D naught, right? So this is the force for in case of flexible devices. Of course, here I have considered the dielectric material to be flexible. You can have case where your electrodes are also flexible. Okay. However, these capacitive force sensors have certain limitations. That's why we see other micro force sensors also in picture. Okay. The biggest limitation of this capacitive force sensor is they can drift over time due to material fatigue. Okay. They also require precision in the fabrication. Okay. Consider that you have this comb structure. Okay. You have this comb structure. Okay. This is fixed one. This is moving. Okay. You wanted to fabricate this comb to be say 500 nanometer of length, and in place of that you have fabricated 505 nanometer, and in one comb you have fabricated say 495 nanometer. Okay. The calculations will be erroneous in this case, right, because the overlapping area and other things will change, right. Similarly, the thickness of this finger is also very sophisticated to be fabricated, particularly in case of lithography. The liftoff of such devices is very difficult. Okay. So this require a precise fabrication technology. Okay. Then note that this force sensor is very susceptible to the environment noise. Okay. It may not be that much effective to environment conditions, but they are susceptible to environment noise, particularly the EMI. Okay. The application of these capacitive force sensors are enormous. Okay. Including some biomedical application like fabrication of force and tactile sensors, for surgical tools. Okay. In robotics, for gripping or gripper force sensing. Then for precision instrumentation, this kind of micro force sensor or nano force sensor are very much required. Then for consumer electronics, that all these touch sensors are using this force and tactile sensors that mostly capacitive. They are mostly capacitive in nature. Okay. So along with that, there are other applications also for capacitive force sensors, and that's why 30% of the force sensor or micro force sensor fabricated is capacitive in nature. Okay. So with this, we are concluding our discussion on capacitive force sensors. We will be discussing other kind of force sensor in our next lecture. Thank you.